Assalamu alaikum everyone. Today we are going to conduct lecture number 22 of our course Microprocessor and Assembly Language, and we are going to start lecture number 4 on Arithmetic Instruction. So let's proceed to our topic. Okay, and today we are going to cover Divisor instructions in 8086 microprocessor. So we will be covering 3 different instructions in this lecture. Very first instruction we are going to cover is DIV, and DIV stands for divide, and it is for unsigned, like we covered mul instruction MUL in multiplication for unsigned numbers. So this time DIV is for unsigned divide, and the format is very simple. DIV S, and S indicates here source operand. So source operand is basically going to be divisor. I hope you know that whenever division is performed, so source there are always two things. One is called dividend, another is called divisor. Dividend is a number which is going to be divided, and divisor is a number which is going to divide the dividend. Or one can also say that division is equal to numerator divided by denominator. So denominator is your dividend and denominator is your divisor. So S is our denominator or divisor. So let's see what is the operation. We have here two cases. In first case, when source operand could be 8-bit, and in second case where source operand can be 16-bit. So as we know that when we are going to divide, there will be two things. One is called quotient and other is called remainder. So we know that when accumulator register is being divided by S8, which is our source operand, and it is 8-bit, so there will be two things in answer. One is called quotient and other is called remainder. So quotient will go to AL register and remainder will go to AH register. And one thing which is to be noted here, that AX contain priorly dividend value or the number which we want to be divided. So that number should be stored AX priorly performing this or using this instruction. And there is a second case where we can use source operand of 16 bits. So that in that case we must know that dividend should be more than 16 bits. So this time we are going to use DX and AX. DX will be holding most significant 16 bits, and AX will be holding least significant 16 bits. So one can also say that there will be there will be two word, one word will be stored in DX, another word will be stored in AX. So combinedly it is 32-bit number, and it is going to be divided by this source operand, which is 16-bit. So again it is a division, and we will be having two different answers. One is called quotient, another is called remainder. So quotient will go to AX and remainder will go to DX. So we are going to see these instruction in emulator as well. Okay, this last column indicating flags affected. So we have mentioned here those which are undefined and which can get affect from these instruction, and you can also verify these things in emulator EMU 8086. Okay, let's see what is our second instruction we are going to cover here, and that is IDIV, which is integer divide. That means divisor should be what? Divisor should be about integer number. So that means IDIV would be format and S will be an integer number, and we will be seeing or we will be observing this effect when we are going to practice this instruction in emulator, and I hope you can do it yourself. I will be doing it for you, but you can practice it yourself. Okay, again there will be two cases. One is called for source operand of 8-bit, another is for source operand of 16-bit. Remaining process, question and remainder things will remain same as we discussed in for DIVS. So it will also be true for IDIVS. Okay, and in the last column we are observing number of flags which can get effect and which can be undefined. Okay, the last instruction that we are going to cover, it is called AAD, or adjustment accumulator register, or adjustment of AL register for division. And one thing which is very important to note here, this instruction should be used priorly division. That means it is kind of, you are setting up your numbers, or you are setting up your accumulator register for the division. That means this addition should be used before this IDIV or DIV command. So what's happening in this instruction, format is very simple. Just you have to write AAD. So by default accumulator will be going to adjust it. And how it is going to be adjusted, it will be actually making it from packed number into unpacked number. And I hope if you remember, we have covered BCD numbers. There are two types of BCD number. One is called packed BCD, another is called unpacked BCD. So this adjustment is basically performing in a way that unpacked BCD is converted into packed. So let's see what is going to happen here. And the procedure is very simple. What we are going to do, we will be multiplying our AH register with 10, and then we will be adding up our AL part. So that is the procedure that one is going to see here in that specific slide, in this specific operation of AAD command. And there will be some flags which are mentioned here for which are going to get effect, and there are some flags which are not going to affect, or which are undefined for this specific instruction. So I hope these details are clear as far as these instructions are concerned from theoretical point of view. So let's see how we are going to see these instructions in emulator. Okay, let's start our first instruction, and we are going to practice it in emulator. So DIV is our first instruction, and let's say we are going to divide decimal number. Let's say decimal number is 4008 T. It is just indicating it is decimal number, and we are going to divide it by 56 in decimal number. So let's convert first this number into hexadecimal. Okay, I hope you know it. So I'm just doing this conversion directly from a calculator. So this calculation would become FA in hex, and the divisor, if it would become 38 hex. So that is simple. I hope this point you can do it. So let's proceed to our, and once we are going to divide, there will be two answers. So question will come into 71 decimal, and that 71 decimal could be written as 47 hex, and remainder, there will be a remainder, and that would be what 32 in decimal. So if we convert it into hexadecimal, would become 20 hex. Okay, so let's proceed to our code. What we are going to do, we are going to move first divided number, which is going to be divided in accumulator register, which is AX. So we are going to move 0FA8 hex, and then we are going to move BL, where our divisor, which is 8-bit. So let's say it is what divisor is 38 hex. Okay, and now we are going to perform DIV BL. So this is it. Let's check our program. Okay, it's ran successfully, so it means there was no error. So single step, 0FA8 is stored, 38 is stored in BL, and once we are going to see, so I hope you can see 47, which was our question, it is stored here in accumulator or AL register, and AH is holding our remainder, which is 20x. So that means question is going towards AL as we were expecting, and remainder is going towards AH as we expected in our operation understanding in our theoretical slide. So I hope this point is clear. Okay, in this slide we are going to do our DIV command, but for a 16-bit divisor. so it process will be almost similar as we did in the last slide, but this time we will be using a divisor which is of 16-bit. So let's say we are going to divide 65,895. the I've chosen this number to be 32-bit, that is why I mean exceeding 16-bit. So 5623 is a divisor, which is of course a 16-bit divisor. Both are in decimal, so let's convert them into hexadecimal. It will become A0 E09, and I hope you can see it. It is not a 16-bit number, it is greater than 16-bit number, so that means we're gonna need more than two register, more than one register that should be 16-bit. Okay, and the next number is 1F7 once we are going to convert our divisor into hexadecimal. So that is of course a 16-bit number, and that is the logic 16-bit divisor. So once we are going to perform this calculation, the question will become 117 in decimal, and once it is going to be written in hexadecimal, it becomes 75x. And similarly, once it is going remainder will be 1062 in decimal, and once we are going to convert into hexadecimal, it will become 426 hex. So let's see how we are going to program it. Our program, first of all, let me put them in comment. Okay, now we can program our code. So first, we know that we need two different registers. So one is going to be DX, that will store the higher part 0000AX, and the lower part will be stored in 0E09 in accumulator AX register, and then we'll be moving our divisor, which is going to be 16-bit. So we were using 16-bit register, which is BX here. So 15F7, and that is also in hexadecimal. Okay, now we are going to use our DIV command, which our source operand, which is BX register, a 16-bit register. So let's proceed. We are going to evaluate. Single step 0A in DX is loaded, 0E09 is loaded. Single step, so BL1F7 is loaded, and I hope you can see it. It's clearly written AX contain what divisor is going to be shown in AX as we see, and remainder is shown in DX as we see in the emulator part. So I hope this instructions simulation is quite easy for you. If you have got any queries, please note them down for our online sessions. Thank you. So let's proceed to our next thing. Okay, I'm going to skip IDIV command. So I'm not going to represent IDIV command because it is almost similar. Division is going to be same, except we are going to use signed numbers for them, and I hope you can do it yourself because we have done this sign calculation in multiplication. So I hope you can do it yourself, and if you have any confusion, you can ask me in online session. So I'm going to skip this command. What I'm going to explain you is AAD command, because it is interesting and bit unique in a sense that it is used prior to the operation, and it is going to convert what should I say, a number which is packed into the unpacked form. So you can say that processing is done on a packed number. So let's see what is going to happen in this command. So let's say I'm using a unpacked number, that could be simple 09, okay, or if it is going to store in AL. Let's say if we are using an unpacked number in accumulator register, so it could be 09. Both are example of unpacked number. Okay, what else we can see? For example, we write 39 in pack, okay, in pack format, that would become what, 0309 in AX register. Okay, and what else? For example, if we write the unpack form, that would be like 009 only, that is that we have already seen in okay, that I have already explained. So let's say we are dividing a number which is in packed form, and we are dividing 19 by 4. Okay, so first of all we have to see what is going to be happen with 19. That is going to be 0109, because it is going to stored in complete AX, or if I explain it clearly, 01 will be going towards accumulator higher part, and 09 will be going towards accumulator lower part. So that is why one can see it is 1 and it is 9, so it is 19 in packed format. Okay, I'm sorry for this notification. Yeah, okay, next thing that we are going to see, we are going to divide it by 4. So 4 will be simply what? Okay, let's convert them. Okay, let's write a program. Okay, move AX comma 0109, as I explained, it should be like this, and we can use simply our BL in 04 hex, which is our divisor, and we can simply divide. But before using this divide, we have to set our accumulator before because this is in packed format, and we have to make it ready for this division command. So what we are going to do, we are going to just use this command AAD, so it will prepare our data present, which is present in accumulator, for this div command, and later we can use div command. So I'm going to explain this explanation. First let me put these things in comment. Okay, comment this block. Yes, I've done it. Okay, so now let's evaluate it. Okay, where is our mistake? Okay, yeah, I'm missing our source operand, which is going to be BL. Okay, now let's re-emulate. Yes, everything is okay. Single step 0109, I hope you can see here in this AX register, and then we are going to press again single step, so 04 is here. Okay, now thing is going to be interesting. What is going to happen once it is going to be in it is going to be executed? So if you remember, what is going to happen, AH part will get multiplied by 10 plus AL, and that will go to AL. Okay, and what will happen with AH will become 0. That should be happening. So why we are doing so? Because 01 indicates 10th position, so 10th should be multiplied by 10, and we are adding unit in it, which is going to be part of AL. So that is why 01 multiplied by 10 would become 10, and 10 plus 9 would become 19, and 19 in hexadecimal would be equals to what? 13. I hope you know it. So 13 will be going towards AL. Okay, this could be our result. It will go into AL, and okay, I'm writing in the wrong position. First of all, let me cancel it here. Let me put it here. Yes. Okay, and 00 hex will store in accumulator higher part, so that thing will be happening. So I'm just removing it. Okay, so let's press this DIV and see whether press this AAD instruction and see whether it is going to work like this as we have discussed or not. So single step, yes, you can see 013 is stored, 13 is stored in AL, and 00 is stored in AH. So now you are ready for this division, and I hope if you remember, you are dividing 9 by 4. That means question will become what? 4, and remainder would be what? The remainder would be simply 3, because 4 4 is 16 plus 3 would be equals to 19. So let's see, is it going to happen or not? Single step, yes, it is correct. 04 is a question which is stored in accumulator AL part. We learned this thing whenever we are using a 8-bit divisor. So AL will contain question part and AH will contain remainder part. So 03 is also stored in as a remainder in AH part. So I hope this example is clear. This is very interesting, that's why I explained it. So I hope now you have 4 adjustment command in your mind. One is adjustment for what? Addition. And for adjustment of addition, we have 2 different, ASCII adjustment and BCD adjustment, or decimal adjustment, right? And similarly, we have ASCII adjustment and BCD adjustment for subtraction, and then for multiplication we have AAM, which is ASCII adjustment for multiplication, and that's it. That is basically AAD is adjustment for division. So I hope this explanation is completely clear. If you have any confusion, please note them down for online session. Okay, that's it from this lecture. Today we covered, and we also terminate our all arithmetic instructions. So alhamdulillah, we have covered all the arithmetic instructions in past 4 lectures. If you have any confusions, combinedly in all those lectures, we can discuss them in online session. So please use these video tutorials fruitfully for yourself, because it is very important for your course. Okay, thank you so much for listening.